Hello everyone, welcome to our channel Wisdom ML. So in this video we'll be talking about how we can detect disaster from just a simple tweet. And it's basically a competition problem in Kaggle. So it's a Kaggle competition problem. And we have used this dataset only, Kaggle competition dataset, that is natural language processing with disaster tweets. So the problem statement is something that when the people tweets on Twitter, right? So sometimes some agencies actually monitoring the Twitter programmatically, okay, like disaster relief organizations, news agencies. Okay, so some tweets which are indicative towards disaster, uh, so that they identify and in that way they can easily provide the resources or relief services once anyone tweets regarding it. Because mostly we understand that because mostly we know that when disaster happens, information regarding that is very important because in that way we can quickly supply services and relief services to the affected place. So that's why it is very important if we develop something like that based on monitoring of just Twitter tweets, that if anyone actually uh, declaring there is a disaster based on his tweets, so programmatically or automatically using NLP, we can detect whether it is actually a disaster or not. But the main issue is that sometimes people tweets in a way that it is actually not disaster, but with the words, the machine will feel that it is a disaster. Like this one, you can see this is the image, and you can see that in this tweet, one plus side, look at the sky. Last night it was blaze. So that's mean is it is actually not a disaster, okay? But the author has used the word ablaze, which but here this ablaze means it metaphorically, not exactly to the disaster. So this is clear to a human actually, but for, actually for the machines it is quite difficult to understand the contextual knowledge of the words. Okay, so that's why we should be developing a very accurate model so that it can understand these contextual knowledge between the words and give accurate predictions based on the sentences. So this is basically a multi-part series of disaster detection video, and in this we are first using machine learning. So in this video we'll be using machine learning approach to detect disasters, okay, from the tweets, and we'll see what performance we can obtain with only machine learning or traditional machine learning models by applying certain NLP based pre-processing to the textual data. And in the next video we'll be again comparing it our machine learning approach with STM model, and later on in the third part we'll be actually uh, comparing all the both approaches like STM and machine learning with per transformers. Okay. So the third part will be very important, and in that part, I will also tell you overall architecture of BERT, what is transformer, how they are actually revolutionizing NLP industry. So let's start today's video. So let me zoom a bit so that you can see the code clearly. So like in any use case, we have to import some Python libraries. So we are importing some basic Python libraries, and apart from that, we are also plotting some plotting based libraries like Matplotlib and Cbon. And apart from that, some basic data processing libraries like Pandas, NumPy. Next, we are also importing NLTK library, because this library will help us in importing or getting stop words, and because it is a very important step to remove stop words. So we should load the stop words first using NLTK library, and then. And apart from that, these are some model evaluation libraries. The rest are very important. That is TF-IDF vectorizer. Okay, so this concept is basically term frequency and inverse document frequency vectorizer. It is a special type of vectorizer to convert textual data or string-based data into numerical format with some weightings. Because if we simply convert our data into document matrix, so it will not solve our purpose, and it will not be much accurate. But TF-IDF provides some weightings so that a machine can understand the importance of certain words based on the process. And count vectorizer is also there, which is the base level vectorizer. And in that, we don't apply any weights. It only counts the number of words present in each and every word. So that's why we will not be using count vectorizer, but it's a complex problem. So that's why we are using TF-IDF vectorizer. Next, we'll be using train test fit and all. And for this use case, we are basically using two machine learning libraries, machine learning algorithms basically. One is passive aggressive classifier, okay, and the second one is multinomial naive Bayes algorithm, because we know that naive Bayes algorithms uh, do pretty well in NLP based tasks, textual data. So that's why we'll be using naive Bayes. Next, what we are doing again, we are mounting our DU and downloading stop word from which are punctuations, word net, model dependency. That is all. So if we see the data, so our data is somewhat, we have the keyword position, then we have a text, and we have a tag. So in this use case, we'll be only using two columns, that is text, which is the actual tweets, and target, which is the label of particular tweet. Whether one denotes disaster, while zero denotes it's a normal. Now, if we see about overall info of the data, so we can see that there are 7,613 records. Okay, and in the text and the target, we can see there is more null entries. Okay. Now, if we see the distribution, so we have quite balanced distribution. So in one, we have around 3,200 entries, while uh, in zero or normal tweets, we have that is for more than maybe 4,200 tweets. Now, if we just want to analyze about the length of the tweets, so that's why we are calculating the length by applying len function or the text column, which is our actual tweet. So in that way, we are actually creating one column with the length so that we can further analyze it within plots. So if we see the overall distribution of the length, so we can see that it actually uh, its maybe higher value is around 125 to 140. Okay, so most frequency is around this, while we have around increasing distribution from 20 till 125 or 130. It is quite uneven. Now, so if you can see, we have an average of 101 words, okay, while maximum is 157. So if we see the maximum length tweet, so you can see that this is the one, and it's quite fuzzy language they used in this tweet. Okay, because these are the actual records or actual tweets from the Twitter. So some type of mixed language you can expect in these types of things. So, some of the things what we can notice here is that there are some you can see when you hyphen apostrophe re, that means you. So these types of keywords we have to remove. So apart from that, we will not be considering these numerical numbers within the text because we'll be only analyzing the contextual information present within the textual data. And these type of words will also generally not on the purpose because if we want to do that, so we have to do open. But presently in this approach, we don't have, so we'll be leaving as it is. Apart from that, we will also we have to remove these type of special characters. So basically, we will remove the special characters and numerical words from the sentences. So if we see class-wise distribution, so we can see that we have in disaster, if we can see our distribution is somewhat towards concentrated towards 140, 130 to 145, where here we can see it is towards 140 only. Okay. And here the maximum value is you can see around 145 we can say, but here our maximum value ranges go to 150. And the reason is that generally when we do some normal tweets, so we use certain words, but whereas if we want to uh, convey any disaster, so our language will be restricted and we will be using only certain words in the tweets. So next, what we'll be doing, we'll be plotting word cloud to better understand what is the distribution of words in both the classes, that is normal tweets or registered tweets. So we can see here. So first of all, we are creating stop as an object, and it will be something a list of all the stop words. And here we are actually in this function we are removing stop words. Okay, so we are actually subsetting our data frame into 1 and 0, means normal and disaster tweets. And based on that, we'll be plotting our word cloud. So in this, we are actually removing all the stop words from the tweets. So the first is our disaster tweet. So as we can see, let me just zoom off and see better. So here we can see that this is the disaster tweet, and we can see some very intuitive keywords used like flood, fire, bomber, death, storm. So which indicates that our data has very uh, intuitive distribution of words, which are actual words generally we use while conveying disaster. So next is our normal tweets. So we can see that normal tweets are somewhat quite obvious that we have normal words like love, people, know, going. So these are very common used words, which is indicative of that we are actually uh, having, which we are actually seeing normal tweets, which are not any disaster. So discuss next. So now the important part is we have to clean our data because we are actually using tweets. So tweets consist of different types of special characters and all, especially at the rate. Because when we tweet, we usually do at the rate and all. So like this one, we generally hashtag do this type of hashtag and do at the rate and so that we actually have to remove basically. So now What we are doing basically, we are creating stop words and also creating lematizer. So what lematizer do basically? So lematizer usually used to uh, trim the words into their proper lemmas. Okay. So what is this is basically so if we have a word like going, okay, which have different form, so it will convert it into its base form, so that that base form should have also grammatical meaning. It should not be something like uh, uh, not a proper English word. Okay, so it lemmatizes basically different uh, variants of particular words into their base form. Okay, so we are first lowercasing our texts. Then we are tokenizing our all the words in the sentences, and after that, because this step is very important, uh, tokenization before applying lemmatization. Okay, because we have to analyze each and every token, and if any token is of different tense or form, it will convert it into base form. So once we have converted everything into words, list of words, so now we are iterating our list of words. And two things we are doing. One, we are lemmatizing each word. And second, we are also restricting that those words should not belong to stop words. So two type of operations are happening. One is a type of filtering, and second is a type of blind lemmatization. Now, if we do both the steps, then because we have done all the operations over individual words, so now we have to join it into a proper sentence form. So in this step, we are actually joining all the words into proper sentence. And this step is very important. Here we have used a regular expression to only consider words which are only alphabetic. So we are not considering numeric or special characters in our data. So this will remove. So we have applied this function clean to it in our text column, and we have created another column that is clean text. So now, so that we can compare. So you can see that we have removed all the stop words, plus we have also uh, cleaned these type of special characters. So this will be our cleaned set of tweets, which we will be actually using for building machine learning. Now we have to create our feature and target variable. So clean tweets is our features actually, and target is target. So we are actually train test splitting and using 80% for training and 20% for uh, testing. Now comes the important part, that is TF-ITF factorizer. So this step will convert our textual data into uh, numeric format in the form of vectors. Okay, with some weightings. So here some of the things we are using, that is stop words is equal to English. Then we are applying max TF is equal to 0.8. So and 1 gram range 1.2. So because we are using bigram, okay. Bigrams means we are analyzing pair of words, because pair of words generally gives us some context, so that's why we are using bigram. And max df is equal to 0.8 means the words which have maximum frequency of, let's say, 80% out of 100%, we are considering those. In the words which are more than 80% frequent in the sentences, we are not considering for vectorization. Okay, because they are pretty common. Okay, so because in vectorization, specifically TF, IDF, our core aim is to use give importance to those words mostly which are unique and which give actual context based on classes. So that's why we are restricting higher frequency words. Okay. Now we have applied using fit transform on train set and using a transform on test set. First we have to fit our model. So base level models are multinomial name base. So here we have to pass our vectorized train, that is TF-IDF train 2, and Y train is our train. Now, next step is we are doing cross validation. So in cross validation, we have used model selection library. And in model selection, we have K4 and we are using 10 splits. So what it does is basically it internally divides our training data into 10 segments, and iteratively it trains on 9 segments one by one and test on the rest segment, it's one segment. Again, this shuffling will happen for different segments until and unless we cover all the segments. Okay. So here we can see we have 79.22% accuracy. This is cross validation accuracy. Now, if we see prediction results, so we are calculating some important evaluation metrics, that is accuracy, precision, sensitivity, specificity, and F1 score. And here we can see that we had 80% accuracy, 85% precision we got. Sensitivity is around 64%, which is quite lower. And specificity we have 92 and F1 score is 72. Now if we see the confusion matrix, so we know that we have more normal tweets. So it actually classified more number of tweets correctly, which are normal. Whereas for disaster, you can see 419 it predicted correctly, but 235 it predicted wrongly. That is, they actually belongs as disaster tweets, but classified it as normal. So that's the issue with this model. So this is the base level multi-normal name-based model. Now we have a specialized model for textual data, that is passive aggressive classifier. And the reason for using is that personally in my different NLP projects, I found that this classifier, this machine learning model algorithm is pretty good in my past experience, and it performs well on textual data. So let's see. So here we got around 78.68% accuracy. And if we see the model prediction, so we have accuracy somewhat lower. This is the overall accuracy. Precision also lower by 10%, but we can see that sensitivity improved by more than 11%. That is good. And in this use case, guys, most of the cases people ask me that what metric is important for any machine learning task. So let me tell you guys, metrics that is important. It depends on the use case. Like in this one, what is our aim? To detect disaster tweets accurately, and most of the disaster accurate. And how it affects basically, because if we so sensitivity is nothing but recall, and here we actually focus more on one, that is actual disease, actual target things which we want to predict. So if a patient suffering from cancer, okay, so if the model is able to predict correctly that the uh, patient is suffering from cancer, then that model sensitivity is high. Okay. So here our aim is to detect disaster tweets correctly, because if someone declares disaster in his tweets and the model unable to predict it, then it will be a mess, because it directly affects human life. Because news agencies and disaster relief agencies will not be able to uh, reach on time to the destinations of where the actual disaster happened. So this is the impact of this model. So you can understand how much important sensitivity is in this use case. So now comes another variants, that is a trigram. So trigram is nothing but a combination of three words which defines the uh, context of something which you want to analyze. Okay, so we can see that here we have uh, uh, we actually pass 1 comma 3, which means we are analyzing trigrams ranging from 1 to 3 tokens. And again, we are fitting our multinomial name-based model. And if we see cross-validation accuracy, it is 78.45%. Now, if we see model prediction, so if we compare with the previous one, so multinomial name-based TF diagram is 79.84% accuracy, which is lower than its previous performance. While precision is somewhat improved and it's higher among all, but sensitivity reduced again and it is lower out. So this is not good fit model for this use case. That is pretty clear. This is also not good model as per this use case. But we can see that our passive aggressive classifier based on diagram performed pretty well, and that's why we say that why F1 score is important, because it is a harmonic mean of sensitivity and precision. So because we have to uh, basically maintain a balance between precision and sensitivity, and based on our use case we have to decide which one is better. So this is the average of all, you can say harmonic mean of all. So this is higher for passive aggressive, 75.48%. Now if we see passive aggressive trying now, so what we are doing is so our cross validation accuracy is around 79.37, and if we compare with uh, bigrams cross validation accuracy. So it was around 78.68. So it means that the model is somewhat getting improved, because with the training set, it is seeing good patterns in the form of diagrams. So now if we see the performance, overall performance, so we can say that here we have more disaster predictions, 499 correct, whereas we have 694 correct normalities, which is okay. So if you see overall accuracy reduced, right, and but the sensitivity is improved, 76.299%. Whereas precision we have 74%, which is lower, right, lower among all. But the best part is that sensitivity is highest. And that's why its F1 score is 75.15. It's pretty close to 75.4. So if we have to choose between these two, so we'll definitely choose this one because we have higher sensitivity, which is the aim of our use case, to detect more number of disaster tweets and with a decent F1 score if we compare. But this is really not a best performance because we have used traditional machine learning models. So in the next video, maybe we'll be seeing how LSTMs, which are more advanced and where we use word embeddings, can help our model to increase its accuracy and sensitivity. And in the third part, we'll be applying a BERT, and we'll see how this pre-trained BERT will help us in getting more accurate results. So now the another important part is most important informative features. So in this, what we are doing is, because in vectorizer we have one feature that we can get the feature names of, which are the actual features which are responsible for particular class. So if we see, so in this function, basically we have to pass vectorizer our actual classifier which we want to analyze, which whose feature we want to analyze, and the number of feature which we want to analyze. So here what we are doing is we are passing our TF ideal vectorizer 3 because it was a best result it has given for passive aggressive model, and we are analyzing only 10 features. So we can see that for 0, that is normal tweets, we have these type of words, Okay. Some of the words are pretty common for disaster. You can see traumatized, mishap, and suicide bomb, whereas others are pretty normal. And if we see here, so it is pretty clear that these words, which are really signifying that it is a disaster, wildlife, fire, forest, flood, bombing, Hiroshima, Japan. So it signifies that it is a disaster. Now, if we can see here also, so in this we are analyzing highest accurate model, that is bigram and with multinomial namespace. So we can see that these words, which is taking into consideration for uh, normal tweets, are not pretty much contextual. But if we see this one, so it is quite contextual. You can see that news, disaster, suicide, uh, but apart from that, nothing else. So we can see that top 10 features differs if we compare it with our passive aggressive classifier. And here the words are pretty relevant if we compare it with disaster words. Now the best part is we want to see how our model, the best model which we have selected, will predict some sample sentences. So we have just taken some sample tweets like just happened a terrible car crash. It's a disaster tweet. Heard about earthquake is different cities. Stay safe, everyone. So these two tweets signifying disasters. Whereas no, I don't like cold. Blues gray. No, I certainly do think the human move to Israel. So it's a normal tweet. So these two are normal tweets. These two are disaster tweets. So uh, now the thing which is very important is we have to use our vectorizer to transform these textual sentences into numerical vectors. Okay, so that's what we are using. We are using our TF-IDF vectorizer 3 and transforming our sentences. Then we are predicting using our past TF3, which is our trigram based passive aggressive classifier. And now we are iterating over sentences and predictions by zipping and passing all the text and label. And we can see that if label is equal to 1, that is, it is a disaster tweet. And we are also printing the text or sentence. And else it is a normal tweet and we are also printing the text. So we can see that it has correctly identified disaster tweets. You can see that, whereas normal, it is correctly identified that these are normal. So this machine learning, traditional machine learning model is also doing pretty well on sample sentences, but uh, in case of complex cases or the words which are metaphor, in that case, it will definitely fail. So that's why we'll be moving towards LSTM and word-based model to see how they will improve our performance. So thanks guys, thanks for watching our video and stay tuned to get some more interesting videos in the upcoming week. Thanks.